Yes. Okay, so I'm very much thankful to the organizers for giving me this opportunity. Today I'm going to talk about this particular paper. So these are my contents basically. So today, first I'm going to introduce about
Thank you.
quantum
So
entanglement
let me
and
introduce Dr.
a
Who should
very
introduce.
restrictive case of a representation of a two-qubit state, a geometric representation of a two-qubit state. Then I will introduce a particular information processing task known as quantum random access codes. Well, there are different versions of these random access codes, and today we are going to discuss about two-qubit assisted random access codes. Then I will introduce what is 2-to-1 random access codes assisted with two qubits. Then how to quantify the quantum advantage in this particular protocol. So there will be a corresponding figure of merit. And then I will discuss that can we gain some quantum advantage in a sequential random access code. Well, that is important in the aspect of communication complexity problem. And then I will try to explain two of our main results, and then I will briefly introduce the summary. So these are my collaborators for this paper. So Deborshida is in University College London now. Shonda is in IIIT Hyderabad. Anando is at OIST Tokyo, and Arubda is doing uh, in a college actually. So they are all all of them actually doing research work. So this paper is published was published in Physical Review A later. So okay, so let us start with the concept of an entanglement. So we already know some aspects of entanglement theory. So if there is a bipartite state means there are two spatially separated labs. They are holding quantum particles. So in this case, a bipartite density matrix rho 1, 2, where 1 is in Alice's lab and 2 is in Bob's lab, it will be an entangled state if it cannot be expressed at the following form. So this is known as the separable form actually. This is nothing but classically mixing these separable states where rho 1 and rho 2 individual, they are density matrices, and this state is said to be a pure entangled if this bipartite density matrix has unit rank. For example, this particular state is a pure entangled state as long as these two conditions are satisfied. Okay, so in in an information processing task, people may ask that whether entanglement is always necessary or not. For example, in quantum teleportation or quantum dense coding or entanglement swapping, in these cases, entanglement is actually necessary. So we cannot gain any advantage using separable states. Separable states mean those states that can be prepared using local operation and classical communication. But there exist other different tasks, for example, random access code. Now in random access code, we have shown that actually if we use a sequential random access code, then entanglement in general is not necessary at all. And we can also gain advantage using separable state also. Okay. So let us start with the, as already the previous speaker already mentioned about the block sphere representation of qubit state. So a qubit state can be mapped. There is a mapping from these qubits, Hilbert's two-dimensional Hilbert space to a three-dimensional unit sphere space. So this is basically a generic representation of a qubit state in block sphere representation. These the small r actually represents a vector that can be at most the modulus can be 1, and a two qubit state has a generic representation that is known as the Hilbert-Smith representation, where capital R and this small r and small a's are known as the local vectors or block vectors for individual parties. For example, 1 and 2. And the last term is known as the correlation matrix term. So this correlation matrix, in general, they contains 9 elements, where each of the elements must be real, and it gives you a number between 0 to 1. So this correlation matrix contains information uh, about entanglement, about discord, or about steering or Bell non-locality, whatever. So they are very vital. Okay. So now I have introduced how to represent an entangled state and what is the generic representation of a two-qubit state. Now let us introduce a particular information processing task where this two-qubit state is actually necessary. So this particular task is known as a random access code. So the basic formalism of random access code is that there will be two spatially separated labs, Alice and Bob, and any random access code game can be defined by a set of numbers, where this first number n is basically represents the input string given to Alice, and m is the number of bits that Alice can communicate to Bob, and p is the guessing probability. So let me make it more clear. So for example, there are two spatially separated labs and some input string of length n, where each of the elements can be either 0 or 1, is given to Alice with equal priority probability. Now Alice and Bob are sharing some initially 2-qubit state. Okay, so their local dimension is basically 2. Now the restriction of Alice is that Alice can communicate only m bits, where m is strictly less than n, after performing some operation on his quantum particle. And depending on Alice's outcome, Bob will again perform some local operation and try to guess every bit of Alice's string with at least probability p. Okay, so this is the basic idea of a random access code. Now, for example, in a 2-to-1 random access code, that means Alice has given 2-bit strings, a length of 2 strings. That means either 0001, 10, or 11. So each of the bit string occurs with probability 1/4. Now, since Alice and Bob share a 2-qubit state, Alice will accordingly measure her qubit depending on the string given to him. So Alice will apply or perform measurement in a measurement operator capital A0, A1, where he will obtain some particular outcome that will be either 0 or 1 depending on the bit string. Then Alice will communicate his outcome to Bob, and Bob will guess actually what Bob actually guess some bit, some 0 or 1, where 0 represents that Bob will guess the first bit of Alice, and 1 represents Bob want to guess the second bit of Alice. So depending on y, Bob will perform some measurement dy that will again give some outcome, either 0 or 1, since these are all dichotomic measurements. After that, Bob or the receiver will perform or calculate some Boolean operation, some Boolean function actually. So this particular Boolean function will be a XOR function of the outcome communicated to Bob and Bob's outcome. So Bob guessing will be accurate if this particular condition is satisfied. That means ay means that Alice's bit actually. ay is equal to the calculated Boolean function. If this equality holds, then Bob's case is correct. Now, even if we use a maximally entangled state, the average success probability in RAC task cannot be one because of the construction of this problem actually. So RAC will be there will be a win strategy 100% if Alice and Bob use some post quantum state. So I will not discuss those things actually. And the 3-to-1 RAC is nothing but a general extension of this particular problem. So that means there will be input string of length 3 and there will be 8 possibilities, and accordingly Bob will compute the same function. Well, now in our scenario, as we have told that it is a 2-qubit assisted random access coding problem. So in this scenario, there are some restriction imposed on the 2-qubit state. The first restriction is if Alice and Bob are playing 2-to-1 RAC, in that case, the marginal at Bob's side has to be maximally mixed. That means if they initially share this row 1, 2, then if I discard the Alice's part, then Bob's part will be in a maximally mixed state. The second condition is that when they will play 3-to-1 RAC game, then there will be no restriction on the state space structure of the 2-qubit state. Okay, so we restrict ourselves only to 2-to-1 and 3-to-1 RAC. So these are our actual basic condition. Now, what is our figure of merit? Now, since it is a kind of information processing task, and we want to show that that this 2-qubit state, if I assist this RAC with some 2-qubit state, it will show some quantum advantage. Then I have to fix a figure of merit. So there are different figure of merits actually exist in literature. For example, the average success probability. That means on average, how Bob's case is accurate. Here we are interested in the minimum success probability. That means in the previous case, there are 4 possibilities. In 2-to-1 RAC, there are four possibilities. So in this case, the least probability where the minimization is taken over the all input string as well as Bob's guess. So the probability of Bob's correct guess, the least case probability we are interested here. This is our figure of merit. Now this RAC protocol is a one-shot process and it is a one-way LOCC protocol. As you can see that Alice first measures the qubit, Alice communicates 1 bit to Bob, not more than that, and Bob will accordingly measure her qubit. So it is basically a one-way LOCC protocol, and it is a one-shot process. So we will gain some advantage if and only if this minimum success probability is strictly greater than half, where the only restriction imposed here that the Bob's marginal has to be maximally mixed if they are playing 2-to-1 RAC. So the permissible range of this minimum value is bounded by this lower bound and upper bound. The upper bound is achievable if they share a maximally entangled state, and if they share some non-maximally or any noisy entangled state, then this value will decrease and we will gain quantum advantage as long as this value is greater than half. And if it is equal to or less than half, then we can actually gain advantage by some classical shared randomness. So now we are interested in a sequential RAC game. So what is a sequential RAC? Now there are a set of players. There are Alice 1, Alice 2, Alice 3, and so on. And there are Bob 1, Bob 2, Bob 3, and so on. Now all these pairs are basically spatially separated. That means Alice 1, Alice 2, Alice 3 are in a same lab, whereas Bob 1, Bob 2, Bob 3, they are in a same lab. Or you can say that there are quantum channels between Alice 1 and Alice 2, Alice 2 and Alice 3, and so on, and so vice versa. Now, the Alice 1 and Bob 1 start with the singlet state, with a maximally entangled state. And they want to play either 2-to-1 RAC or 3-to-1 RAC, depending on the criteria. For example, let us consider each of the pair of players want to play 2-to-1 RAC game. So in this case, Alice 1 will perform some measurement, some general POVM measurement, and communicate one classical bit to Bob. And depending on Alice's outcome, Bob will again perform some POVM measurement. So this POVM operation actually will not decrease or reduce the quantum correlation shared in the singlet state. But if you measure in projective measurement, then the state will exactly collapse and entanglement is lost. But we will show here that entanglement is not necessary at all in the view of this particular figure of merit. Now, after Alice 1 and Bob 1 completed their 2-to-1 RAC, Bob computed their function and make the correct guess. Then Alice 1 will send her particle to Alice 2, and similarly Bob 1 will send her particle to Bob 2. Then they will individually perform a 2-to-1 RAC. So they are independently performing RAC, and this is a sequential game actually. And we are interested that how many Alice and Bob can win this game actually. So what is the setup? Oh, so there is a typo here. There will be Alice 1 and Bob 1. So Alice 1 and Bob 1 share a singlet state, a maximally entangled state. So they start with a singlet state where every Alice K and Bob K performs unsharp measurement or TOVM measurement of this particular structure. So for individual K, where K runs from 1 to N, so these lambda K are the sharpness parameter that depends on the K actually. So this is a single parameter family of POVM. Okay, so and these are the restrictions that these set of the sharpness parameters must be in this range. Okay, so this set of POVM measurement has to be chosen in such a way that every kth pair, the shared state will be of this form. So this is actually a Bell diagonal form. So in general, this is we cannot say whether it is an entangled state or not. It can be separable as well as entangled. Now this is a Bell diagonal state. Why it is Bell diagonal? Because if we do a spectral decomposition, the eigenvectors will be in standard Bell basis. Now why we are using this particular structure? Because if they want to implement 2-to-1 RAC, the restriction was that on Bob's side, the reduced density matrix will be maximally mixed. And for 3-to-1 RAC, there was no restriction. So for this particular class of state, both 2-to-1 and 3-to-1 RAC will be satisfied actually. So actually, this is our basic result. The first lemma is that this is actually a necessary condition that let Alice K and Bob K performing into one RAC, where N is either 2 or 3, assisted with a 2-qubit Bell diagonal state, as I have mentioned earlier. Then they will achieve quantum advantage in every RAC round if this condition is satisfied. So these conditions do not say whether this Bell diagonal state is entangled or not, but this condition is necessary for quantum advantage. So now one may say that even separable state also showing quantum advantage. the answer is yes in general. Because separable state also can carry some quantum information in form of quantum discord, and using that discord we can win that game actually. So this is actually a resource minimization task, and following this lemma one can actually implement the main result, that is our theorem, that unbounded pairs of Alice and Bob can demonstrate or show quantum advantage in 2-to-1 RAC assisted with a 2-bit share the state from a common source and having a maximally mixed marginal and at the receiver's end. And it can be also one can also conclude for 3-to-1 RAC game. That means infinite times I can infinite, or you can say unbounded number of times I can gain quantum advantage. That means the minimum success probability for each round will be greater than half, where this condition has to be satisfied. That means you can equivalently say that those states, those shared 2-qubit states must possess some kind of quantum correlation that is not possible using a pure classical theory. And that quantum state do not have to be an entangled state at all. So this is basically a weak criteria. Well, there are some corollaries which can be found or followed by this lemma and theorem. The first one of the corollary is that suppose a subset of players Alice 1 and Bob 1 want to play 2-to-1 RAC with some probability pk, and the other players want to play the 3-to-1 RAC game with probability 1 minus p. So in that case also one can show that unbounded number of times I can gain quantum advantage. So I am not going to the technical details because these, as I mentioned earlier, that these are the POVM elements, the structure of the POVM elements, and these are the post-measurement state at every round. And for every round, we have to check the minimum success probability is greater than half or not, where in every step the state has to be in Bell diagonal form. Okay. So now, what is the main summary of our result? So we know about communication complexity problem. One definition, there are many ways to define communication complexity. One way communication complexity problem is that suppose there are two spatially separated parties or players, and individual players have been given two different bit strings. For example, Alice and Bob, where Alice is the sender and Bob is the receiver. Alice has given some bit string of length n, and Bob has given some bit string of length m. Now, Alice will perform some measurement, and they may use some additional shared entanglement. Now, depending on Alice's measurement and communication, Bob will perform some operation, and finally, Bob will compute some binary function. So, there are many ways to calculate binary function. Now, if there is some referee, so the referee knows what will be the value of that particular binary function for some given x and for some given y. If the value, Bob's computed value, matches exactly with referee's argument, then we say that in that game Bob actually wins with some probability. So in that case, if the average success probability is greater than the classical bound, we actually comment that we gain some quantum advantage in this communication complexity problem. Now there are some cost optimization. Now one way to think that the communication cost, that means Alice communicating bits to Bob, we can either reduce that for a given entangled state, for a given copies of entangled state, or other way, one can say that Alice can communicate any amount of classical bits, but the shared entangled state or the shared resource state or the any shared two-qubit state has to be least entangled, or it can be separable at all. So in that case, our problem actually shows that it actually minimizes the communication complexity cost if I can assume that the sequential RAC game is a particular represents a particular subclass of a one-way communication complexity problem. In that case, one can show that one can gain quantum advantage without using any shared entangled state at all. So, but yes, of course, that if the state is separable, then that is not sufficient. Actually, the necessary condition is that that separable state has to satisfy some property that I have discussed. So this was our work. So okay, thank you.
So thanks for the beautiful talk. So now our session is open for question. Audience can ask question now.
Hello.
Yes.
So I was wondering that the functional, the Boolean function that you have chosen,
Yes.
uh,
Yes.
the XOR function,
Uh,
instead of that function, if any other Boolean function were chosen, then the probability for success will it vary?
yes. Yes.
I mean for classical, what is the limit for quantum advantage if I change the particular Boolean function?
Yes. This is a very nice question actually, because their Boolean function can be calculated in various ways. Here we have calculated the XOR function.
Right.
That means XORing the output state of Bob's guess and the input from Alice. So for this particular class of Boolean operation, there will be restriction on the additional, I mean the shared resource state and the amount of classical communication. Okay. So if I actually change my function, for example, combination of the basic logic gates, then also I think one can show that these constraints will vary actually. So I cannot say clearly what will be the exact limit, but whatever I can show that I can say that if this Boolean function is a XOR function, it will always give you one if Alice and Bob share some PR correlation. That
Oh,
means in that case, Bob will exactly guess every bit of Alice for any 2-to-1 RAC game actually. Okay, so there, but PR correlation is not actually it is a post quantum correlation.
okay. Thank you for the nice talk.
So since we are running out of time, we are unable to take